Hello everybody, welcome back to another video. Today we're going to be solving a really daunting problem, so let's get right into it. So for today's problem, we have the integral from 0 to 1 of x times the square root of all of this, and inside that square root is x, times the cube root of x, times the fourth root of x, and so on and so forth. This ... means that this goes on for an infinite number of terms, making this integral pretty difficult. So let's see the solution. Now, on your first instincts, you might think, hey, there might be some clever u substitution that we can do here to solve this problem. So commonly in Calculus 2, you're taught that you want to let the most complicated part of your integral equal a variable u. Now, to adequately replace this part of the integral with a u, you need a differential to integrate with respect to. So respect to this variable u, and we call that du, similar to dx. So that's why this is called u substitution. This is probably a review for many of you, but when you're finding du, it's just like how the name sounds. You want to differentiate whatever you set to that variable u. You want to just differentiate that and see if you can replace something in the existing integral with that du. But if you look at what we set to u right now, as I just marked right here, as this entire radical that goes on for an infinite number of terms, differentiating u will only complicate this further. So we can't really find anything more complicated in the integral already. So it doesn't look like u substitution is going to work. Now, what if we tried u substituting something else? If we tried u substituting this thing, we have the same issue, because what happens is this continues as the fifth root, then x times the sixth root, and then so on and so forth. So the same issue arises that whatever this derivative is, which I'm not going to find, it's pretty weird, but we can't find it anywhere else in the integral, because it's all kind of weird, because this square root 2 is spanning this entire radical, like all of these terms, these infinitely many terms. It's not like it's the square root of x, it's not like this. So it's not structured like this or something. So we can't do some funny multiplication or split it up. So what can we do? Now you might think, hey, there's some integration by parts that we can do here. Oops. If we say, so integration by parts equals this. This is the formula. Integral of u dv equals uv minus integral of v du. Now I can do a proof on this. It's quite simple using the product rule for derivatives. But essentially, you'll notice here in our formula, we have a dv existing in our original integral, and then we'll want to integrate that v, and then we're going to integrate whatever that is. Again, so whatever we have dv, we're going to integrate dv to get v, and then we're going to integrate it with respect to du. So just like that. Now, is there something that's easily integrable in our current integral? Yes, we do have x that's easily integrable, but if you notice here, the other variable, whatever we set to u, which would be this in this case, that would, right here in this part of the formula, the integration by parts, we're going to be doing du to find this integral. So I'm assuming this is a review for all of you, but if we did set this to be our u, once again the same issue arises. How are we going to differentiate something so diabolical? It's so weird. So let's look at some other solutions. Maybe instead of u substitution or trig substitution, I didn't even talk about that, but it won't work out, and I can do a different video on that, or even integration by parts, maybe there's some other handy trick we can do here. And it turns out that's true. So I'm going to be rewriting this integral just using some exponents instead of these fancy signs of the radicals. All right, so we're going to say that this is equal to the integral from 0 to 1 of x. Now, what is the square root of x? The square root of x can be denoted with a power, a fractional exponent, like this. It's x to the power of 1/2, just like that. So we can say that this is equal to x times, I'm going to switch to green, x times x to the power of 1/2. Now, be very careful here. When we're looking at this x, sure, the cube root of x is equal to x to the 1/3, as you learned in algebra, basic algebra, but this entire cube root is under a radical itself. It's under the square root. So what does that mean? It's essentially like this term's power, this specific x's power, is equal to the square root of the cube root of x. So this would be this, and this would equal x to the 1/3 to the power of 1/2. And what would this equal? X to the 1/6. Now, I'm not saying that this entire thing, this entire square root with all of these terms is equal to this, or you can simplify or replace it anywhere, but I'm just saying the power of this x is 1/6, because you have 1/2 right here and 1/3. So that's just some basic algebra rules like that. Now, that means I can continue. I can write that this is x to the 1/6, and let's keep going. Now, let me use orange. This x right here, that's under the fourth root, what do we do about that? The power of this x, or the exponent, would be, we start from the very outside, this square root, then the cube root, because this cube root continues all the way over here, over the fourth root, and then this fourth root. So that means that the power would be this. It'd be the square root of the cube root of the fourth root, and this is just equal to x to the 1 over 4, to the 1 over 3, to the 1 over 2. And this is how we rewrite it like that. So it goes like out and then inwards like that. Now, when we're dealing with exponents, I'm sure you learned this, but you can just multiply exponents when you're raising an exponent to another exponent in this manner. Specifically like this. This is not equal to, just this little sidetrack, it's not equal to this. This would mean you go in reverse order in this case. X to the 1 over 4 to the 1 over 3 to the 1 over 2 means that you take 1 over 3 to the 1 over 2. Whatever that is, you just keep that as a blob, and then you take 1 over 4 to that blob, and then you name that a, and then you take x to the power of a. So that you go in reverse order from top down. But except with this one, you want to, with the parentheses, you want to follow the order of parentheses and order of operations. So you find the fourth root, cube root, and then 1/2, like that. Or you can just multiply it using standard rules of exponents. So what do you get now? Using this, I'm going to, instead of writing whatever that denominator is, I'm just going to write x to the 1 over 4 times 3 times 2 times 1. And I'm going to write the 1 in for a reason. And you'll notice here, I'm going to rewrite the 6 as 3 times 2 times 1. And I'm going to rewrite this 2 as 2 times 1. Do we see any pattern emerging? Now, I have not continued and written out all of the terms of this infinitely long integral, because remember, there's an infinite number of radicals inside of that. Now, but can we see any pattern emerging with these x's to generalize this? And in fact, we can't see a pattern. So this is x to the 1 over 1. We see x to the 1 over 2 times 1, 1 over 3 times 2 times 1, x times 1 over 4 times 3 times 2 times 1. Then you multiply by x to the 1 over 5 times 4 times 3 times 2 times 1, and so on and so forth, dx. And these are all multiplying. These are not adding, so you can't say that. Now, I'm going to clean this up a little bit. So this is equal to the integral from 0 to 1, x times x to the 1 over 2, just like that, times x to the 1 over, what is 3 times 2 times 1? Now, this is commonly taught in geometry, sometimes in algebra, but if you have a number, like 3, for example, and it's decreasing by 1 until it gets to 1, and you're multiplying all of these numbers, this is equal to the starting number factorial. So 3 factorial is defined as 3 times 2 times 1. And I did a separate video on the gamma function, which is the generalization of the factorial to different decimal numbers and even fractionals and fractions and all of that, and possibly even negative numbers. And you should check out my video on that. But for the purposes of this video, just know that a factorial and factorial is equal to n times n minus 1 times n minus 2 ... until you get to 1. So if this gets to 1 faster, then just go to 1. Yeah. So now that we know what a factorial is, we can replace this 3 times 2 times 1 with 3 factorial. Then we can write times x to the 1 over 4 factorial times x to the 1 over 5 factorial ... dx. Just like that. Okay. Now I'm going to move all of this to the left-hand side right here, because now things get really interesting. Now, I'm going to clean this up a little bit more. Now, when you have, this is basic algebra, of course, but when you have something x to the power of a times x to the power of b, if the bases are the same, then what I can do is I can simply write x to the a plus b, the exponents add. So what this means is I can rewrite this integral as the integral from 0 to 1 of x to the 1 plus 1/2 plus 1 over 3 factorial. And by the way, this 2 I can represent as 2 factorial, even though it's 2. But for clarity's purposes, I'm going to be writing it as 1 over 2 factorial, and then plus 1 over 4 factorial, plus 1 over 5 factorial, plus ... So this ... gets moved into the exponent because we're multiplying all of these different terms with x in the base. Now what happens? And don't forget our differential, very important because we are integrating. What do we notice? I'm going to once again clean this up a little bit more into some more fancy notation, but don't worry, it's not too complicated. So this symbol is called the sum or a sigma, many ways of calling it. But this is the sum from n equals 1 to infinity of 1 over n factorial, just like that, dx. Okay, now you'll notice something quite interesting. Oh, by the way, for those who don't know about the summation, if you don't know, I'll just talk about it really quickly. It's essentially a for loop if you do programming or any sorts, but if you don't know what that is, you just start at this index right here, you plug in that index into this formula, so you get 1 over 1 factorial. Then you want to add a plus sign, and then add 1 to whatever that value of n is. Now n is equal to 2. Then you want to plug it back into this formula, 1 over 2 factorial, add your plus sign, and repeat. So you do this until, and when do you stop? You keep going until n is equal to your top number. But if we say n is equal to infinity, that means that this is an infinite series, and this goes on forever. So we're adding infinitely many terms. So I highly suggest that you have some basic calculus knowledge or series or algebra 2 knowledge before delving into this, and I can make some videos on that if you want me to. Now, if you recognize this and you've taken calculus 2 before, you'll know that this is a very, very special series, and you'll see why. Because in calculus, we're often taught that the summation from n equals 0, not 1, n equals 0, of 1 over n factorial is equal to a brilliant number by the name of E, just like that, E. That is right. That is Euler's number. Yeah, that man Euler said that 2.71828818 ... or I think something like that, is equal to this summation right here, 1 over n factorial. It's quite beautiful, isn't it? Because you have a factorial involved, super simple, yeah. Now, if you don't know where E is used, I could literally go talk for hours on where this number is used. It's absolutely insane. It's used literally in all of mathematics without you even knowing it. It's used in real life to interest formulas, in finance, in compounding. It's used in complex analysis. It's used literally everywhere. It's used in sine, cosine, literally every trigonometric function. It's insane. There's so many things. There are an infinite number of things you can do with E. But I'm not going to be talking too much about that. I can do a separate video on that if you want me to. Now, with this new knowledge at hand, and by the way, you can prove this. There are a number of ways to prove this, but this is a pretty fundamental knowledge in calculus, so I'm assuming that everyone knows this. So let's move forward. Now I can write this as the integral from 0 to 1 of x. Remember, the n starts at 0 in the definition for E using this sum. Now, what happened? Let's write out the first few terms of the sum to see how we can substitute this in right here. If we let n equal 0 with this sum right here, we have 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus ... If we simplify this a little bit, we have 1 plus 1 plus 1 over 2 factorial plus ... 0 factorial is 1. That's a video for another day. I think I already did a video on that, so check that out. But given this knowledge, you can see how our previous sum was 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. And this is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus ... So we have an extra 1 right here. Now, what does that mean? That means that we can substitute E for our exponent, except we have to subtract this 1 because that 1 is not present. We can just do that, and we're good to go. So if you see here, it's just equal to the same sum, but since we're starting from one step forward instead of n equals 0, we just have to subtract that 1 when substituting E for the sum. So now we're good to integrate. Is there anything we're missing? We got E involved, we got the -1, and we've handled all of these infinitely many terms, and we found the sum, so there's nothing infinitely long to worry about. Now we can just say this is equal to, what is the integral of x times e to the e minus 1? You just want to add 1 to your exponent and divide by your new exponent. So we can say that this integral is equal to x to the e, to the e over e. And what are our bounds? Our bounds are 0 to 1. Now we'll just simply plug in our bounds. Fundamental theorem of calculus. We can say that this is equal to 1 to the e over e minus 0 to the e over e. Simplify a little bit, we have 1 over e, because 1 to the e is just 1, and then 0 to the e over e is just 0 minus 0. And ladies and gentlemen, this brings us our answer, 1 over e. Absolutely amazing. That means that the integral from 0 to 1 of x times the square root of x times the cube root of this entire, I'm not going to say that monstrosity again, but this entire infinitely long thing, just with increasing numbers of radicals like this, from 0 to 1, involves e, that magical number that shows up everywhere. I hope you enjoyed today's video. Let me know if you have any questions. If you want me to go faster next time, let me know. If you want me to go a little slower or explain something, that's also very helpful. Let me know in the comments. Any future video ideas? Absolutely. That's what the comments are for. Drop a like, follow. Thank you guys. See ya.